Today we're going to keep going down the path of talking about waterside HVAC systems. But today it'll be somewhat of a, um, well, it's a topic that's highly related to the hot water and chilled water systems that we've been talking about. So today we're going to talk about pumps, and we're going to keep talking about VFDs, or should I say, we're going to dive deeper into VFDs. So we've kind of avoided talking about pumps so far, beyond just saying, hey, all these waterside systems we're talking about require pumps. Anytime we're moving water through a building, we have to have a pump to do that. Chilled water systems need a chilled water pump. Hot water systems need a hot water pump. Condenser water systems need a condenser water pump. You're probably seeing a pattern there. And there isn't really a difference between those. It's just they're moving, well, they're all moving the same fluid, really, water, namely. They're just using it for different purposes. So some are moving hot water, some are moving chilled water, some are moving condenser water. Pumps in HVAC systems, most often, I mean 99% of the time, they are centrifugal devices, just like fans. And when I say centrifugal devices, that means that they create flow in the system through creating a pressure differential, just like a fan would, a centrifugal fan. What this means is that all the same laws of VFDs and EC motors, when we're talking about the affinity laws and what happens when we change the speed of a fan or a pump, all of those same laws apply because the fans and the pumps are all centrifugal devices. The derivation of pump horsepower functionally is the same as our derivation of fan horsepower. And I didn't walk you through how we arrived at those fan horsepower equations, but when we look at how the pump horsepower equations are built, you're going to see a lot of similarities, a lot of the same DNA as compared to the fan horsepower. And that makes sense because these are both centrifugal devices, fans and pumps. They're just moving different fluids. One is moving water and one is moving air. Similar to fans, pumps have one job: move a certain flow at a certain pressure differential. Analogous to a fan, which has one job, which is move a certain flow in CFM at a pressure differential in inches of water column. So it's doing the same thing, moving some flow at some differential. It's just doing it in different units. Here's a breakdown or kind of a sectional cutout of what a typical centrifugal pump looks like. We have our motor shaft, and you can see it's directly mounted to the pump impeller right here. So you'd have a motor attached on this side that's not shown that would spin this motor shaft, which spins this impeller. This would be your pump outlet on the top and your pump inlet coming in right there. So think back to a fan impeller. As this thing spins, it creates an outward pressure that forces water outward, out the top here. And by doing that, creates essentially a vacuum in the center of the impeller, which will then induce some water draw in. And sort of the same thing over here, just illustrated. What this looks like actually out in the field would be something like this. Although it's not often you see the pipe fancily colored like this. We have our motor. We have our horizontal inlet into the pump, and the motor shaft is hidden underneath this yellow sheathing, I guess, to protect it, to maintain safety. So that'll spin this impeller. You have water coming in the side, and you have water coming out the top. And this would be what's called a base mounted end suction pump. So the term base mounted is just because it's attached to the ground, because you can have a pump that is light enough to just sit off the ground and just be, say, hung from the ceiling, or sometimes just supported with the connecting pipe. But this is a base mounted end suction pump, and it's end suction because it's pulling in water off of the end of the pump. Or you could have an inline pump, which would have no change in flow direction, as opposed to the base mounted end suction pump, which does have that flow direction change. And you can see that the inline pump is configured a little bit differently. We have the motor that sits on top, meaning the shaft is running vertically and the impeller is spinning on the horizontal plane. Your water's coming in on one side and it's leaving on the other side. These two styles of pumps are configured differently, but fundamentally they're still doing the same thing. They're spinning an impeller, which creates a pressure differential to flow water through this piping system. Let's talk about the horsepower equations. So fan power versus pump power. We know our fan horsepower equation, CFM times inches water column divided by 6,356 times the products of all of our efficiencies. The pump power equation looks like this. Our pump horsepower is equal to our GPM, gallons per minute, times our feet of head divided by 3,960 multiplied by the product of our efficiencies. And when you look at these two equations side by side, you can start to see the similarities. We have our flow, CFM and GPM. We have our pressure differential, inches water column, feet of head. And then we have a constant in the denominator that's going to be based on the fluid type that our device is moving and based on our numerator units. On the air side, because we're using cubic feet per minute and inches of water column, and we're dealing with air, which has a certain density to it, if you looked at the derivation of this equation, that all works out to 6,356. And then if you go through the same steps on a water-based system, using GPM and feet ahead, you end up with 3,960. And there's the products of efficiencies. So these equations are really rooted in the same things, just different fluids. Similar to fans, there are typically three ways that we can express the horsepower of a pump. We have our water horsepower, which is based on flow and pressure only. This would be analogous to air horsepower on a fan, which is based on CFM and inches of water column. So the water horsepower is our useful delivered work. That is the job of the pump. Deliver some flow at some pressure. So that is our water horsepower. Brake horsepower is going to be the same, regardless of if it's a fan or a pump. This accounts for the impeller efficiency, and this is the motor shaft output. So as a reminder, just lock this in your heads right now. Brake horsepower. It's all about what does the motor shaft have to output to get whatever water horsepower or air horsepower we need at the ultimate outlet of our device. And then we have motor horsepower, which accounts for the pump inefficiency, the motor inefficiency, and anything else. So if we had a VFD on our pump, that would be another efficiency that we'd need to plug in here. Or if we had a belt drive system, belts have losses as well. Motor horsepower, total power input to deliver that water horsepower. So again, that water horsepower is the job of the pump. That's what we need at the outlet. Our water horsepower is just based on flow and pressure. Brake horsepower, same equation, but now we've brought in the efficiency of the pump, or you could say the pump impeller, same thing. And then the motor horsepower, we're adding in the motor efficiency and other stuff that we might have. VFDs, I mentioned this already. The principles of controlling pump speed with a VFD, the same principles we talked about with fans, are also going to apply here. Same concepts, just different fluids. As a reminder, affinity law 1, ratio of the pump RPM will be equal to the ratio of the pump flows. So if you have the RPM, you have the flow. The second law, the ratio of the pressure differential is going to be based on the ratio of the flow squared. So if we have our flow, we'll have a quarter of the pressure requirements in the same system. And the third law, ratio of the horsepower is equal to the ratio of the flows cubed. So same affinity laws that we've talked about with fans also apply to pumps. But similar to fans, there are some pitfalls we have to watch out for. We can convert constant flow pumps to variable flow pumps and save energy. And we can save a lot of energy based on that third affinity law. And it's a good idea to do these conversions. Or maybe if you're designing a new system, you could ask the question, well, does it make sense to make this pump a variable speed pump, or should we leave it as constant volume? But you can't just put a VFD on a pump motor and expect energy savings. If you think back to when we talked about VFDs with fans, and we talked about some specific systems, specific air side systems where we discussed how if you put a VFD on this type of system, what else do you have to do to make that VFD actually work? Because as I've explained to many maintenance personnel over the years, you can't just slap a VFD on something and then just get energy savings out of it. It's not this magic thing that just saves energy. You have to think about the entire system and what is actually going to cause that VFD to reduce its speed. For pumps specifically, you need to look at the control valve configuration. Constant volume pumps. So recall that these pumps are, let's say we have a hot water system. These pumps are sending hot water out into the system to all of these hot water coils at our air handlers. And at every one of those hot water coils, they have what's called a three-way control valve. And that's what's used to vary the flow through the coil. Some water is going to go through the coil where it'll actually heat up the airstream, which is the goal of our hot water system. But some of this water is just bypassed right back into the hot water return. And what this allows is for us to modulate our heating or our cooling capacity, depending on what type of system we're talking about, but it keeps the total flow constant. So let's look at a visual representation. So we have this heating coil right here. This is our, say, our hot water coil. This solid line here, this is our hot water supply. Let's say we're sending 50 gallons per minute to this heating coil. And if we're sending 50 gallons in, well, we have to be getting 50 gallons out on the return side. The thing is, though, we can't just send 50 gallons per minute through this coil all the time. What if that space doesn't need 50 gallons per minute? What if it's a moderately cold day and at that moment in time, they only need 20 gallons a minute? If you were sending 50 gallons a minute all the time to that heating coil, you would end up overheating the space. So the purpose of this control valve, which is this funny looking device right here, and here's what it would look like in the real world. This is a three-way control valve. And you can probably guess that because it has 3 ports on it. And this big thing on top, this is our actuator that is going to open or close the valve. So if we look at this, we can see we have a split right here. We can send some water to the coil, or we can send water straight into the bypass. And as this actuator opens and closes, it will either send more water to the heating coil and less through the bypass, or vice versa. Which means this bypass right here is always going to be 50 gallons per minute minus whatever our coil flow is. So we can use this device to vary the flow through the coil, but we are maintaining a constant flow overall coming to and from this coil. So that three-way control valve, we're either diverting water away or we're allowing more water through the coil depending on if we want more heat or if we want less heat. So if we have too much heat, divert more flow away. If we want more heat, allow more flow through the coil. But either way, we have constant total flow for the pump. If we have 10 of these three-way valves out in our system, even though every one of those valves is varying flow at the coil itself, it is still constant flow to and from each coil, which means the pump flow overall will be constant. So that's three-way control valves. Now let's talk about two-way control valves. Two-way control valves are what are used in variable volume pump systems. Two-way control valves, they also allow for that modulation of our heating or our cooling capacity control. But the difference is these valves allow the total flow to vary directly with the load. The way they do this, they take out that bypass leg. And now we're just going to vary the flow through the coil, and that's it. So what does that look like? You can probably figure out why they call this a two-way control valve. You only have 2 ports on here. And you can see the bypass leg here is now gone. So now this valve can open or close, but it's either going to allow more flow through the coil or less flow through the coil. So now our supply coming in, now that is a variable flow. In the previous example for three-way valves, that was 50 gallons per minute all the time. Now, our total supply is anywhere from 0 to 50, meaning our coil flow is 0 to 50, and our return is 0 to 50. So the two-way control valve can now vary the flow through the heating coil, but it's also varying the flow overall in the system. Similar concept. If we have too much heating going on, close the valve a bit. But if we need more heating, allow more flow through the coil and open it a bit. But the big difference here is that pump will now vary our total flow depending on all the system needs. So by taking out that bypass leg, now we can actually turn this into a variable volume system at back at the pumps. If you have a pump VFD, those are controlled, at least typically, they are controlled off of a pressure differential transmitter, or a PDT, in the system, just like a VFD controlled fan. If you think back to when we were talking about VAV systems, and you had a bunch of VAV boxes, you stuck this PDT in the ductwork, and as the boxes started to close because they're calling for less air, that PDT would see an increase in pressure because now you're choking off your air and the pressure is going to increase accordingly. And that increase in pressure will send a signal to the VFD to tell it to slow down, and vice versa. As boxes open up, that will decrease the pressure in the duct, and then that will send a signal to the VFD to speed it up. So it works very similar here, except instead of VAV boxes, we have these control valves that are allowing or restricting our water flow. So if you put a VFD on one of your pumps, assuming it's a constant volume system and it has a bunch of three-way control valves, just because you stuck a VFD on the pump doesn't mean that that pump is going to do anything if you don't replace the three-way valves that are out in the system. Because that VFD is dependent on the changes in the pressure of the pipe. But if you have all three-way valves, that means they're all constant flow and you won't see any pressure changes and the VFD won't do anything. So the pressure in the system isn't going to change as those valves open and close because the overall flow is still constant. Also, this is somewhat review, same as fan motors. If you're upgrading a pump, that motor has to be inverter duty rated or else the VFD's going to burn it up. The motor's not going to explode or anything like that, but within months or maybe a year, it'll be toast. It's got to be inverter duty rated. So normally what we do, we normally don't put VFDs on existing pumps. You could do that as long as you replace the motor, but what we do more often is we just replace the whole pump and motor assembly and then put a VFD on that. Interactive effects. This is going to keep coming back. So again, just like with the fan, we have interactive effects that we have to worry about whenever we're saving pump energy. If we're talking about hot water systems, I'm going to go through this somewhat fast because I'm hoping this is sort of review back when we talked about it with fans. It's the same types of concepts. If we're saving energy at the pump, what does that mean for the fluid we're conveying? Are we trying to keep the fluid hot or are we trying to keep it cold? In a hot water system, the goal is to heat up the water. And if we are putting in electrical input, that actually helps because ultimately that input energy gets converted to heat. And hey, we're trying to keep the water hot anyway. So it's not a complete loss there. And so if we reduce the pump energy in a hot water system by turning it into a variable speed pump and we slow it down when we don't need all of that flow, now we have to heat up the water just a little bit more to make up for that energy that we're no longer putting into the water. So it's the same exact idea as a fan serving an HVAC system when it's in heating mode and it's actively calling for heat. One difference though, compared to fans, the motor itself is not in the fluid stream. So the 10 to 12% of waste heat, because motors are around 90% efficient, that waste heat doesn't actually enter the fluid. To put it into a picture, this is a motor with a belt drive that's driving a fan impeller, and you got your fan casing in here. So if you're staring right at this, this is the fan inlet. And this whole box around here is the casing of the air handler. So if our air is coming in from off screen over here, this is acting as essentially our ductwork. Then it's getting pulled into the impeller inlet right in here and getting pulled into this fan casing. And then it'll get blown out through this duct on that side. So what you can see here is in a fan system, this motor is actually sitting in the path of the airstream because it's inside the air handler cabinet, which is acting as our ductwork. So all of that motor heat that's coming off the motor is still going into the air. That 10 to 12% waste heat is still entering the airstream. And then the other 90-ish percent, that's going into the impeller where it's moving that air, and that impeller energy will ultimately become heat as well. So in a fan system, all of that input energy going into the motor turns into heat in the airstream. Converse that with a pump. So we have our water coming in. This is the same picture as before. Our water coming out, but now our motor heat, that 10 to 12%, that is now going into the space. You could argue that, well, maybe that's still not going to waste because maybe I'm trying to keep that space at some temperature. And that would be a correct argument to make. But when we're isolating our focus on the hot water system, that motor heat is not entering the fluid stream. So we would only have the impeller energy going into the fluid stream, that 90% of the motor input. So it is somewhat of a subtle difference. We're only talking about 10 to 12%, but 10 to 12%, that's not exactly a small number, especially if we're talking about a very large motor. Quick example. Again, I'm going to move through this kind of fast because this is kind of review. If we have 10 kilowatts of pump total motor power and it's a 90% efficient motor, that means 9 kW of that is going to go into the water, and then 1 kW will just go off as heat into the space. And if we stick a VFD on that pump, reduce the speed, and let's say now it's going to require 6 kilowatts. So our raw pump power savings, 10 minus 6, 4 kW. The heat that was going into the water before was 9 kW because of that 10% that we're not accounting for. And the heat going into the water after is 5.4 kW. And so the difference there, we were putting in 9 kW, now we're putting in 5.4. So that delta, 3.6, that needs to come from somewhere. If it's a heating system, we'll have to make up that heat. So we saved 4 kW on the pump power, but now our boiler needs to provide an additional 3.6 kW to make that up. If the boiler is gas fired, then we still get some positive cost savings. And I underlined cost because we're not getting positive energy savings, because going from electric on the pump energy side to gas on the boiler side, there is an efficiency loss there, but we will still see some cost savings. If our boiler is electric resistance, then there's no gains at all. What's the point? You shouldn't be converting an electric hot water system to variable speed control because you will see no savings. So make sure you account for the heating penalty because this is going to derate your savings. Your savings won't look as good if you are dealing with a hot water system, because anytime that hot water system is running, you are going to see a heating penalty. There's no benefit that could be seen in other seasons because this hot water system is entirely devoted to heating the building and will only be running when it's heating the building. On the chilled water side, the goal is to cool the water. And so if we reduce that electric input energy, that also means we don't have to cool that energy by the chiller. So now we're saving pump energy by reducing the pump speed, but then we get some bonus cooling energy savings on the chiller because now the chiller doesn't have to work quite as hard. Using the same numbers, 10 kW motor, 90% efficient, meaning 9 kW goes into the water, 1 kW just enters the space as heat. We reduce that pump speed. Now the chiller doesn't have to work as hard. The raw pump power savings, again, 4 kW. And then the heat that was going into the water before, same as the last example, 9 kW. The heat entering the water after, 5.4 kW, and the difference being 3.6. So all the same numbers, except now this is a cooling system instead of a heating system. Again, the raw pump savings, 4 kW, but now we've taken off 3.6 kW of load off of the chiller, and that is heat that no longer needs to be cooled. If our chiller COP at this moment in time happens to be 3.0, you take that load, divide by 3.0, and we can say that we've reduced the power consumption of the chiller by 1.2 kW. Our total savings will be our pump savings plus our chiller savings, which will be 5.2 kW. So on this chilled water example, we got this nice 30% bonus. As compared to the heating system, where we were paying a penalty every time that pump was running, every time we reduced the speed of the pump. Anyway, in this case, every time we're reducing the speed of this pump, we're seeing this nice little extra bonus. And this is why VFDs on chilled water pumps are going to have better overall savings compared to a hot water pump. And that is assuming that all other things are equal, meaning the flow and pressure and the pump and motor efficiency. If you have a highly mismatched hot and chilled water system, like let's say your chilled water pump is only 2 horsepower and your hot water pump is 20 horsepower, the hot water pump will probably still be a better opportunity there just by the nature of it being so much larger. But if they're the same horsepower pumps, chilled water pump VFD upgrades are always going to have better payback because they always have this nice cooling system benefit that gets tacked onto it. So let's dive a little bit deeper into VFDs. And this is going to apply to fans and pumps. Because again, they're really the same devices, just moving different fluids. And some of this is review from a few lectures ago. When we're looking at the affinity laws, the condition 1, condition 2, they have to be looking at the same system. So same ducts. If we're talking about a fan system, same pipe if we're talking about a pump system. You can't use these laws to compare completely different systems. The affinity laws are also based on idealized conditions. And I mentioned this back when we talked about VFDs the first time, that this is all pie in the sky, idealized conditions. And this isn't actually how it's going to work. If we're using a power of 3, if we're using that cubic relationship to estimate our fan power reduction based on our airflow reduction, this is going to overstate savings, because that power of 3 is based on the idealized conditions, and in practice, that's not what we're going to see. So ultimately, it is better to derate using a power of 2.5 or maybe even 2.0. So instead of doing a cubic relationship, you take it to the power of 2.5 or 2.0. I mean, using 2.0 would be, well, that would be a squared relationship, and that would reduce your savings a bit and make it a little more conservative. And but it depends on how aggressive you want to be. There are a couple reasons why we can't reach this ideal condition, why we can't use the cubic relationship. Reason one, VFDs, they have some minimum operating pressure requirements. Meaning, and this is a broad, somewhat vague statement, if we drop the pressure too low, if we go down to those very low VFD speeds, that can cause some operational issues with the pumps. Another reason is motors get less efficient at lower loads. If you think back to when we first talked about motors, I said motors like to be loaded. And if we are reducing the pump or fan speed, we are effectively deloading the motor. Now we can still significantly reduce the operating power of the motor, but we are going to reduce the motor efficiency, meaning more of our energy going in ends up as waste heat. We can still see significant reductions in the total power, but it just won't be quite as good as that cubic relationship, just because we are going to drop efficiency. So if we have lower VFD speed, that means less load, lower motor efficiency. And this all applies to fans and pumps because, again, just to drill it in one more time, same concepts, different fluids. To try to visualize this, if we were to try to look at an actual versus an ideal power reduction relationship between a fan and the airflow reduction, well, if we're at 100% fan speed, we're obviously going to be at 100% power. This orange line would be an ideal cubic relationship. So you can see, even if we get down to 70% load, I mean, we're already down at about 30% fan power. And then it just goes lower from there. So that would be our ideal process. But if we had an actual application, and let's say that application had a 20% minimum pressure requirement, this is more of what that actual curve would look like. So you can see we're not quite saving as much as we would hope, and that becomes more and more stark as we get down to lower speeds. And the difference between these, that would be our overstated savings if we were to use that cubic relationship instead of something more like a squared relationship or a 2.5 power relationship. Last topic, then I'll let you go. I mentioned that virtually all pumps in HVAC, and fans for that matter, are centrifugal devices. They move a fluid by creating that pressure differential. That's a fundamental part of what makes a centrifugal device centrifugal. There is another type of technology, though, that's called positive displacement, or PD, and that is a different way to move fluids. That's not a centrifugal device. Positive displacement devices are going to move fluid physically by just pushing it. They are just pushing fluid volume through a system. They're not doing it by creating a pressure differential. They're just physically pushing it through. And what that means is the affinity laws don't apply to positive displacement pumps like they do for centrifugal pumps. If you have a PD device, you can still vary the speed. There's no reason you can't. If you have a speed control device on it, then the power and the speed are going to be proportional. So half speed equals half power, quarter speed equals quarter power, etc. We've talked a bit about refrigerant compressors. Every DX system, whether it's an air conditioner or a chiller, has a compressor, and that's the thing that's doing the lift or the work. If you think back to the baseball analogy, the compressor is home plate. Most of those compressors in DX cooling and DX heating, if you have a heat pump, are positive displacement devices. And that's how they are moving the refrigerant through their cycle. If you have a larger chiller, those might have a centrifugal compressor, but that is typically only seen in pretty big chillers where the economics actually make sense to have a centrifugal compressor and then to put a VFD on that compressor, which then you could take advantage of the affinity loss. But most refrigerant compressors are positive displacement and they don't follow those rules. They're not very common in fans and pumps, but just keep in mind that not all fans and pumps are suited for VFDs. Or rather, that a VFD might not give you as much savings as you would hope for. This would be an example of a positive displacement pump. So it's called a lobe pump. So these two paddles, I guess we'll call them, these just spin and they just physically push water. So they push water around the outside edge, which then joins up right here and then just gets pushed through and then works its way through the system until it comes back the other side. So this isn't creating flow through a pressure differential. It's just physically pushing the water through the system. And so because of that, the affinity laws are not going to apply. Any questions on that before I let you go? All right, I will stick around for 20 minutes or so if anyone wants to work on homework in the background or ask other questions. Otherwise, have a good weekend and I'll see you next week.
Thank you.
Thank you.